Okay. Exam is Friday. So, what did we do last time? Did we have it in here? Do we have it somewhere else? The timing was different, right? Did we come early? We came early. Whatever we did last time, we're doing that again. So I just need to refresh myself on what we did. And then for those of you who absolutely can't get out of other conflicts, we'll individually make arrangements for you to take the exam. But we'll do the same thing we did last time. And that's this Friday. So we're working on, what are we working on? Maybe? Oh, this doesn't work as a good cursor. There we go. So what are we working on? We're working on writing, open form, net accumulation functions, in closed form. All semester long, we've been writing open form net accumulation functions, letting GC do the work for us, using function notation to find values of those functions. And then we saw some motivation for why we want closed form, that we could have a formula that can rapidly generate results quickly and easily. Open form doesn't do that. Okay? So we're going through a series of techniques for different kinds of rate functions, right? We're looking at different kinds of rate functions, and we're saying if it's the rate function is like this, we've got a technique for that to get the closed form. Okay, so of the net accumulation function. So let's kind of review that. So first we had undoing the chain rule. And what does the rate function have to look like to qualify for undoing the chain rule? So the rate looks like what? Looks like a composite function. Right, so it's the chain rule, right? So that the rate function has to look like something that's just gone through the chain rule. So that means derivative of the external function with the internal function as it is times the derivative of the interior. And so that's the key. That's this relationship right here that gives us that tips us off that it is undoing the chain rule. If the derivative of the interior function is the other factor, right? So that other factor is the derivative of the inside, or off by a constant multiple, then we've got it. We can do undoing the chain rule. And we said this is kind of like the most common one. We see this, so you see this kind of the most, and we should always ask this question first. Is it undoing the chain rule? Okay, and then I have a slide for undoing the product rule, so we'll skip to, what was the next thing we did? Partial fractions. So what kind of rate functions qualify for partial fractions? What kind of rate functions qualify for partial fractions? Rational functions, right? One polynomial divided by another. That's the first. That's a rational function. One polynomial divided by another. Second criteria. Degree of n is less than degree of d. And if it's not, what do you do? Remember what you do? If degree of n is greater than or equal to d, you start by long dividing the polynomial, right? But if the degree of n is less than the degree of d in a polynomial, and then there was one more criteria. Remember? What's that? Yeah, and what allows that, right? So what allows it to be written as a sum of fractions? There's something about our original fraction that allows it to be written as a sum. Yeah. Yeah, so this denominator has to break up into at least two factors. If you've got all three of those criteria, then you can use partial fractions. So the reason I'm reviewing this is so we can learn each skill, but then there's an additional skill that comes along when we've learned all these techniques that you're just going to be given one, and you have to figure out what applies, right? So there's this additional skill besides just learning each technique individually. So that's why we're reviewing this, right? So you need to have like an identification skill, because on the exam, you're not going to be told what technique applies, and you have to come up with that. Okay, so then we did undoing the product rule, and so let's look at common forms of that. Questions on undoing chain or partial fractions? Okay, so undoing the product rule. So with undoing the product rule, you're mostly looking for common forms. You're mostly looking for these common forms. So this is a really common form. Some x to some power times sine, or that could be cosine, right? X to some power times sine or cosine. That was actually the very first example that we did. We did 4x times cosine, or something like that. Okay, likewise, powers of x times e. And that was the second example we did. We did x squared e to the x, or something like that, e to 3x or something. These are the kind of ones we're on the lookout for undoing product rule. Okay, we did natural log in class. And we said, well, that's not two things multiplied together, but there's only one way to set up f and g prime that makes sense. Because if you make natural log g prime, then what happens? Then within that technique, you have to do this antiderivative, and that's what the question we're asking in the first place. So you have to make ln x f. And then we saw powers of x times natural log of x. We said this was different than those first two up above, because the first two up above, how many iterations of undoing the product rule do we need? N of them, right? It's like nested in itself n times. If you have x to the fourth, have fun, right? You're going to do undoing the product rule within itself 4 times. You got to keep track of all that. Won't ask you to do that, but you should know that that's what would happen. What about x to the fourth times ln of x? Yeah, so that you do the derivative of natural log, and you don't have natural log anymore. You have a power of x, and so things react very nicely. So no matter what your n is here, you only have to do it one time. Okay, and then the last common form is, I guess I didn't write it down here, is inverse trig functions. So just like the natural log, you could have like an inverse trig function. And you handle it the same way you do natural log. So is that whatever function you get? Is that going to be the f, or is it going to be the g prime? It's got to be the f, right? If it's the g prime, you don't know. That's the question you've been asked to find the antiderivative. So you're going to, whatever that inverse trig function is, you're going to make that f, and then you follow it through, and then the new integral that you get as a result of the, right? So we do fg equals integral fg prime plus integral, and the whole point of undoing the product rule is this is something attainable or easier, whereas this isn't immediately attainable. So then we solve for this indirectly, right? We do f times g minus the other term of the product rule, right? Yep. So if you set f equal to that, then what times, what's your multiplier? What's your other factor? Okay, so those are the 3 main techniques for harder antiderivatives that we've done so far. Any questions? Okay, so that was your review for the quiz. Here's your quiz. You're going to do the first step of each of these. Just the first step. Get out a sheet of paper. Just the first step. Enough that so someone looking at it would know that you know what to do, but then stop, right? So this is an identification, right? Identification, what's the first step for each of these. Okay, you ready? Okay, grade your own. Here we go. First one. So I rewrote it this way. This is helpful. Remember, if you see like that, this is what it means. What technique is this? Technique is this. Chain, right? Chain. Undoing chain. So first attempt would be? So all your written homework last Wednesday did dozens of these, right? Dozens of these. Focus on Exhibit A or Exhibit B? B. And then to undo it, we just focus on exterior function and do antiderivative, right? That's the first attempt. So what is it? Cosine x to the third, and we need a. So that could be our first attempt. Undoing the chain rule. Undo the chain rule. So we just stop right there. So, and then if you actually keep going, what do you need to finish this? Yeah, you'll need a negative, right? You take the derivative of this, and you'll get negative sine x, not positive sine x. So our second attempt, then we can throw the negative on. If you can get the negative on in the first attempt, that's the goal, right? You just write down the answer. That's the goal of that. That eventually you can just write down the answer the first time. Okay, this one. Yeah.
Would be that partial, it's the f prime of g x, right? The product rule one, right?
Product rule, right? Product rule. And so the first step would be to assign f and g prime. F would be what?
Your f would be x squared.
X squared, because we want that power to go down. When we take the derivative, we want the power of that to go down. It makes a simpler new integral, g prime then assign. There's their first step. Undoing the product rule, first step is assign f to be x squared, g prime to be sine x. Next one. I got arctan of 3x. Identify it as, first step. What do we got? What's that? She wants product. Is it product rule? Yep. Remember, I just said you look for inverse trig functions. Inverse trig functions, and how do we do it? What's f and what's g prime? F is arctangent. G is? G prime, I'm sorry? 1. Undoing the product rule. Next one. X times e to the x squared. Notice, interior function, x squared. Is x the derivative of x squared? Essentially, yep, the power is right. That's all we need. We need the power to be right. X squared and x. Therefore, undo chain rule. First attempt, antiderivative of e to the something. E to the something, first attempt. Two? 1/2. Yeah, so if you can see the 1/2 on the first attempt, good. Or if you can't, what do? You take the derivative of the first attempt and you compare it, and then you alter the first attempt, right? But the goal is you can see that 1/2 right off the bat. And just write down the answer. Okay, last one. Hopefully easy. Partial fractions, first step. Split it up as a over x plus 2, b over x plus 1. Yeah?
So you don't have to long divide in the numerator.
Oh, yeah, good call. Very good. I didn't notice that. Yes, first step is to long divide. Long divide. That's the real first step. Minus 20 for Ashbrook, 80%. Long divide first. Okay, any questions on the quiz? Okay, give yourself 100. Great job. Any questions? Yeah.
Why would you
Because we got the same degree top and bottom. You have to have to be ready for partial fractions, the degree of the numerator has to be strictly less than the degree of the denominator. If it's greater than or equal to, you want to long divide first. Yeah. Yep, so you're going to multiply out the denominator, so it'll look like this. So the real first step is this. Here's the real first step, right? X squared plus 0x plus 3. And then write x squared plus 3x plus 2. And start long dividing. That's the real first step right there. So yes, multiply out the denominator. And then you're going to divide x squared plus 0x plus 3 by that denominator. Okay, any other questions? All right, so next technique. So the next one is looking at more complicated trig integrals. More complicated trig integrals. Here's the deal with those. Here's the game plan. So that rate function is going to be more complicated trig something, okay? And so the goal with these is always you're going to simplify or change the form of the rate function. So we're gonna work on that, and we're gonna simplify it or change its form using either trig identities, and I'll show you the list of basic identities in a second here. So one way that we'll change the form or simplify or rearrange is using trig identities. And the other way is just simply algebra arithmetic. Factoring things out, dividing numerator and denominator, multiplying things out, just algebra. Okay, so why are we doing that? So the goal of doing that, changing the form, is in order to set it up for something simple or straightforward. You'll get maybe you get lots of cancellations, and then you end up with something easy like cosine x, and you can just do it, right? Or you're rearranging, simplifying in order to set up for undoing the chain rule. So you're working with this given rate function using identities or algebra and arithmetic to achieve one of two goals. Something easy, or you're setting it up, you're staging it for undoing the chain rule. That's what all these boil down to, all right? All these more complicated trig integrals boil down to that. So let's review the trig identities that you're going to need for these, the most important ones. And this is a very short list. First of all, basic definitions, right? Upper left here. Basic definitions, tangent, cotangent, cosecant, and secant. And one common technique is going to be to rewrite. So if you have, not always, but if you have cotangents, secants, and cosecant, sometimes a common technique is to rewrite those all as sine and cosine. Get the whole thing in terms of sine and cosine. Or tangent, any of these four. Okay, not always, but that's a common practice. Okay, then we got the Pythagorean identities over here. And that all begins with sine squared plus cosine squared equals 1. But then to get these other two, you're going to divide everything by sine squared or divide everything by cosine squared, and it gives you these other two versions. Okay, so if I divide everything by sine squared, I get 1 plus, what, cosine squared over sine squared is cotangent squared. 1 over sine squared is cosecant squared. And likewise, if I divide everything by cosine squared, I get that second one. Okay, so those are the Pythagorean identities. Half angle. So this is the half angle identity, but actually kind of rearranged because there's really no half angles here. There's a double angle in there. So it's kind of a rearranged of the half angle formulas. These are going to be key for antiderivative of sine squared and antiderivative of cosine squared. And then finally the double angle identities, sine of 2x, sine of cosine x. There's one version of sine 2x. There's actually 3 different versions of cosine 2x, and those are based on the Pythagorean identity. So if you take this and you apply the Pythagorean identity, you get these other 2 versions. Okay, so those are what you have to know. For the exam, so in terms of, do I have to memorize them? Yes, so here it's like I'll kind of meet you halfway. And this is not much, guys, this is not much. So, but here's what I'll do. I'm gonna put on the cover sheet of the exam, I'm gonna put this exact thing right here, but all the right-hand sides of these are all blank. So before you start the exam, you're just gonna fill it in. So yes, you memorize it, you fill it in, and then you'll have that as a reference, as like a formula sheet for the whole exam, okay? So, and that'll be a little bit extra credit, only like point of extra credit to do that, okay? But again, so these you should already know. This you should already know. I told you how to get these from that, okay? And then, so really the memorization is just this bottom half. You could get this done in 5 minutes, okay? All right, questions about identities? All right, so let's look at some examples here. There we go. Okay, I can't see that one off. Cosine squared, tangent squared. Okay, so we got this is a more complicated trig rate function, and we need to work with this, either identities or algebra, to make it something simpler that we can just do, or we're trying to set it up for undoing the chain rule. So what can we do? So you look at our list of identities, or is there any algebra we can do to change the form of this? Yeah.
You could write tangent squared x as sine x cosine x squared.
Okay, so rewriting tangent squared. So actually there's kind of 2 choices here. We could use the Pythagorean, we could write it as secant squared minus 1, or we could write it as this thing squared. And so the better choice is what he said, what Kenny said. Do sine x over tangent x cosine x squared. And did that help? Because they go away, right? So we got cosine squared x, numerator and denominator, it goes away, leaves us sine squared x. Okay, so here's the deal. Sine squared x and cosine squared x are kind of like their own thing that you just have to be on the lookout for and memorize. This is the one thing that kind of breaks the mold of these trig integrals. If it's just sine squared x and nothing else, if it's just sine squared x and nothing else multiplied by it, except a constant multiple, that's fine. But if it's just sine squared x, you do half angle formula. So what is this? And this is, you just kind of remember it and be on the lookout for it. Okay? It's kind of like this, it's kind of like the trick that you have for this. So 1/2, 1 minus cosine 2x. So when it's just sine squared, just cosine squared, you don't use Pythagorean. You use half angle, and then this is something we can do now, right? So you can pull up the 1/2. Antiderivative of 1, x. Antiderivative of minus cosine 2x. So antiderivative of cosine. Sine.
And since you have 2x, you're going to have to multiply.
Right, but this is like a mini undoing the chain rule problem, right? We're also going to need a 1/2, right? We're going to need a 1/2 for that. And then, what does it mean that there's nothing on the top or bottom of the integral sign? What does it mean? Yeah, we use the plus c. It means what? All possible net accumulation functions, starting from any x value a. Any x, any x equals a, we start from. And depending on the a that we start at, gives us a different plus c, right? Because that plus c is the same as minus f of a. So just remember, that's what you're doing with the plus c. You're saying you're counting for any possible starting x value a. And that plus c is just the same as minus f of a. Okay, questions on this one? So again, this is just kind of a fact that you have to memorize and always be on the lookout for. Whenever you have antiderivative of just sine squared or a constant times sine squared or a constant times cosine squared, you just have to have this memorized and be ready to use the half angle formula. But if that sine squared is multiplied or divided or added to any other trig function, then this doesn't apply anymore. Okay? So what do? We use a trig identity. We got a simplification. We got something easy that we could do using another trig identity. Okay? That was what happened here. Questions on this example? Good? Okay. Next one. Okay, I'm going to give you a couple minutes on this while I take attendance. Again, what's the goal? The goal is use algebra and identities to either get something simple or stage it for undoing the chain rule. Okay, go. Okay, Erica, how did it go? Okay, then what? Did you make any progress from there? What can you do? So what, can we simplify that? What is 2 sine x cosine x times cosine x? What is that equal to? Like a shorter version of that. Cosine squared, right. It's 2 cosine, so it's cosine squared. Okay, did this help? Why? Undoing the chain rule, right? You see that? What? Essentially, so you got this composite function. Sine x is essentially the derivative of cosine x, which is the interior. That's what we need for undoing the chain rule. So, first attempt is what cubed? Cosine x cubed. We need a 1/3, and we need a negative. Oh, and we need a 2, right? So we have a 2. That 2 just carries down. This 1/3 is for the 3, and then derivative of cosine x is negative sign. So we need a negative sign for the negative sign. Done. Any questions? Ask if I lost you, if we lost you. Yeah?
Will there be potentially examples of this where you like the trig identities that have product rule and then product rule?
No, it doesn't really. It's all really about undoing the chain rule. Yep. Other questions? can I erase? Okay, going, gone. Okay.
Secant to the fourth, tangent to the
Seventh. Okay, so here's a harder one. Okay, so again, that's the goal with these. The goal is rearrange, simplify, using identities in algebra to get something easy, or stage it for undoing the chain rule. Okay, so when you think about the relationship of secant and tangent, we think about the derivatives, right? So what's the derivative of, yeah, derivative of tangent is secant squared, right? How can we use that fact to think about staging this for undoing the chain rule, right? If the derivative of tangent is secant squared, then what could we do here to kind of set this up for undoing the chain rule? Anybody have an idea? So how does a derivative come into undoing the chain rule, right? So g prime f times f prime. So we think about if secant squared is the derivative of tangent, how would that fit into undoing the chain rule? What would we be looking for trying to do? Yeah. Right. Good. Yeah, so if f prime is the derivative of f, well, so it's kind of like we want an interior function to be what? Tangent. And then the f prime to be? If this were tangent, we would need this to be secant squared, right? So can we get this as secant squared times something, first of all? Can we get this all as secant squared times something? Secant squared times what? Another secant squared, because that gives secant to the fourth. And then? Now, in order for this, that's a square, by the way. So in order for this to work, then everything in those brackets has to be what? If this is going to work. Everything in those brackets has to be something to do with tangent, right? Because tangent's derivative is secant squared. So it's like this interior for our chain rule has to be all tangents. So if we can get all tangents and then secant squared there, then we're getting it ready for undoing the chain rule. Do you see it? So how can I make this? We got 7 tangents already, but I got the secant squared, and I need to make that, if I can make that into tangents, that's good, because then my derivative of tangent is this secant squared out here for undoing the chain rule. Are you following me? Does it make sense? So I need to rewrite everything inside the brackets as tangent. Can I do it? How can I rewrite secant squared in terms of tangent? 1 plus tangent squared, Pythagorean identity, right here. Do you see that? So I can write tangent squared x plus 1 times tangent to the 7th. Did that help? Now I can distribute. I have the first term is tangent to the 9th. Second term is? Do you see what's happening? What's this now? That's secant squared times tangent to the 9th. Can you do it? And then secant squared times tangent to the 7th. Can you do it? Yeah, because secant squared is the derivative of tangent. We've just set it up for undoing the chain rule. So first attempt. So we think about secant squared times tangent to the 9th. What will be the first attempt for undoing the chain rule? Tangent to the 10th. And then also, what else do we need with a tangent to the 10th? 1/10. Is this clicking or not? Or did I lose you? And then secant squared times tangent to the 7th. What will that be? Tangent to the 8th. What else do we need? 1/8. Okay, please ask. I know this is a little bit harder, but the idea is staging, setting it up for undoing the chain rule. Meaning, if we had any power, so here's the power, any power of tangent times secant squared, it'd be undoing the chain rule, right? Any power, g prime, any power of tangent times secant squared, we could undo the chain rule. Yeah, please.
What happened to secant squared x in the last one?
I did the antiderivative, right? So what happens? So if you have, this is undoing the chain rule, right?
Yeah.
When you have undoing the chain rule, two factors collapse into one. The g prime becomes g, and then the f prime goes away, and you undo the chain rule. So that's just what happened. Other questions? All right, so how about try cosine cubed sine to the 5th. Let's do sine to the 15th. See how that goes. See if you can get that one going. So looking at this one, what do you think the f and the f prime will be? What will be the f? What will be the f prime? Nope. You could do that, but that'll be a long nightmare. Yeah.
I'm not sure if this works, but I made it into cosine times sine to the 5th, and then parentheses to the 3rd.
No.
No?
Yeah, the idea is that we're going to pull out a derivative to stage for undoing the chain rule. So what will that derivative be that we pull out? Just cosine x, right? Just cosine x, because the derivative of sine is cosine. And then we'll have what? Cosine squared times. So now inside the bracket, any powers of sine will work. Any power of sine will work because we have the derivative of sine, cosine, as that other factor. So we'll have to change this into sines, and then we're just like this one. So cosine squared equals 1 minus sine squared. And then we got it just like this, right? We'll have sine to the 15th minus sine to the 17th. And both of those work with cosine to do undoing the chain rule. What? 1. Is that right? Did I do it right?